Al-Hallaj. I am the founder of All Cell Technologies and visiting research professor of chemical engineering at the University of Illinois. I will be presenting to you today about the recent development on lithium-ion battery pack safety, and we'll talk a little bit about thermal management. The outline of the presentation will be typically, we will discuss history, future roadmap. We will go over a little bit of the recent mobility or electric mobility application, some of the improvements in lithium-ion battery cost reduction, thermal management. We'll go over some current solutions that are commercially available, and then discuss the past thermal management that we developed at All Cell using phase change composite. We'll present a couple of case studies, and then we'll conclude with some remarks about the current status of lithium-ion battery safety. The major challenge that we see probably today is how can we transition from an oil-based transportation system to an electrified or electric-based drivetrain system. We believe that this is the best solution. Currently, oil or liquid fuels have kind of a monopoly on transportation technologies, whether it's passenger vehicles, ships, trucks, or even airplanes. And the best way to move away from that is to electrify the transportation system that allows you to actually power it by various types of electricity from various sources, renewable and even non-renewable. The way to do that is, as I will show in the next few slides, it's gradual, sometimes full transition to electric-based system, and hybrids can also play some role. And these will be powered by batteries, ultracaps, and in the near future, maybe fuel cells and hydrogen. The main challenges today are batteries are still expensive. The cycle life is not as expected. We'll continue to hear some improvements, potential improvements, but the reality is they're still not there. There's also a question about drive range, which is reflected in energy density or power density. However, lithium-ion batteries have been making very good stride in the past 10 years, 20 years, and they are promising, but it's still, there's some room for improvement. In the near future, you probably see talk about fuel cell and hydrogen as part of the hydrogen economy. I just want to point out that while this is promising, it's still expensive, and there's a lot of issues about robustness and performance of fuel cells for especially passenger vehicles. However, the main challenges still are, fundamental challenge of hydrogen storage on board to provide 300 to 400 mil. That's not just an investment challenge, but it's a fundamental science challenge. And also the infrastructure, there's probably going to be a while before the infrastructure realize where we have hydrogen, generation, transportation, and even deployment or gas, hydrogen stations that you see everywhere. It's been clear that the recent few years, the movement to electric vehicles has taken off. You see this evident in combination of countries and even states like California announcing either complete phase out or continuous push for regulation that push for zero emission vehicles. And we have also seen the industry responding aggressively. Various companies have announced either introduction of various types of electric vehicles, or even some of them announced completely going electric in the foreseeable future. Just to give you an idea about the various challenges that batteries or power system in vehicles, you're looking at here just a map or just a kind of description of what is the electrified drivetrain on vehicles look like. As you can see in this graph, it goes all the way from to start-stop battery that basically power auxiliaries when you stop at traffic light, all the way to fully electrified systems that are powered by batteries or fuel cells. And you will see also in between there's plug-in hybrid, which is a fully electric drivetrain that drive 100% electricity, and then you have a generator, a small generator, that after the vehicle first 20 to 40 miles, then that kicks in and power the vehicle. And in between you have the mild hybrid all the way to the full hybrid, which you see that. This is interesting because even with the micro hybrid or start and stop, you can see that there's significant boost of efficiency that is encouraging for the industry, and it justified the investment all the way to complete electric and zero emission from the vehicle itself. Here's an overview of what's going on. Let's call it a race. There's a race here by all companies to go to the electrification of vehicles, and you'll see generations after generation of vehicles that are now becoming mainstream, and you continue to see that, and companies now creating platforms, and it's just racing to be the first to get market share. Another type of electrified application that is going to be, probably you'll see it a lot more in these days, is electrification of what's called unmanned or autonomous vehicles, as well as electrified airplanes. To the left here, see commercial drones for package delivery, electric boats, autonomous vehicles, all the way to what's called the electric flying taxi, or some form of electric vertical takeoff and landing. That you'll see a lot of those touted. They're still in experimental stage. They're prototypes. We've been involved in a few of those, but we don't see this going to be dominating the cities and neighborhoods anytime soon. But it is part of the plans for the future of transportation. Here's just a kind of a summary. This is probably a little bit of a description of where the industry is going, the battery industry. Lithium-ion has been making very significant improvements over the last 10, 20 years. They kind of dominate the energy storage market today, and their power and density and energy is improving, but most importantly, the cost, as I will say in the next, or show in the next slide. Beyond lithium, we're going to start seeing some technologies like lithium air, lithium sulfur, and the foreseeable future. But in between, there's a huge push towards solid state battery. And those are, the promise here is that the idea of eliminating liquid electrolyte or gel electrolyte lithium ion, which is the key source behind some of the safety problems that the lithium ion battery have. And this technology has been introduced in some application. It's expected to grow. But I'd probably guess that it's going to take a while, probably 5-10 years before solid state technologies and other battery technologies such as lithium or lithium sulfur becomes manufactured and commercialized in high volume. This is one of the driving force behind lithium ion batteries commercialization in a lot of mobility and storage application of renewable energy. As you can see here, this cost of solar energy has dropped significantly, especially over the last 10 years. And in some cases, actually, it's cheaper than conventional sources. That is important because for lithium-ion batteries and other energy storage, because as we've seen in look at areas like California, once the solar energy or renewable energy penetration becomes high enough, it starts disrupting the grid, and it starts causing problem that without storage, you will not be able to further deploy or increase the market share of solar or renewable energy such as wind. So the storage technology goes hand in hand, and that's what we've seen significant improvement in the lithium-ion battery, both performance and cost. And we're going to continue to see that as it goes into both renewable energy application as well as mobility application, as we discussed earlier. We're going to talk a little bit now about thermal management and safety of lithium-ion battery. And just to give you an idea, I'm not going to dwell on this, but just to make sure that this is lithium-ion batteries, are sweet spot is around the human body temperature. And that is where the desired operating temperature should be, or designed to be, to maximize life and optimize performance. Once you go above that temperature, you start going in the 40s or 50s and above that, you start seeing side reaction that will actually degrade the battery fast, and the battery start losing cycle life very quickly. And I will explain a little bit about the root cause of that. But if you exceed that, you go above this temperature, then safety becomes a big concern, and that's what we will discuss in a few slides. To the left of that, if the temperature of the battery is not controlled within that optimum, you start seeing sluggish chemistry that affect the battery performance, and at some point, the electrolyte, the liquid electrolyte, as I mentioned earlier, in those batteries will freeze, and you will not be able to pull any more power or energy out of those batteries. So, this is where any engineer, battery engineer, looks for to, how can I keep the battery in that sweet spot where it performs at its best, and also do not risk cycle life or safety. Here's some of the studies we've done. This work we've done recently as part of our effort to deploy more and more lithium-ion batteries in smart grid application. The graph to the left shows you the impact of temperature. Once you go from 25, you can see that lithium-ion batteries start degrading in a very accelerated rate. And also even the slightest change of voltage, cutoff voltage, for example, if you go from 4.2 volt to 4.1 volt, which is, instead of doing 100% state of charge, you go to 90%, you start also seeing significant improvement in life. And the graph to the right shows you that that's mainly because of the increase in impedance, or what's called resistance. And that's the main culprit for a lot of the challenges that for battery performance and cycle life. We've done a little bit work on that. We've done extensive study with the National Renewable Energy Lab. We published that work, and you'll see a lot of this. This is not unique to us. Most people in the electrochemical field or batteries understand that you can actually quantify the effective temperature, C rate, depth of discharge, and use that with smart battery management system to actually maximize the life of the battery by both controlling the operating condition, but also by controlling the window that you operate the battery to give you the desired life, cycle life, or calendar life. Now, the main challenge here is that when you do that, you have to oversize the battery, and that becomes a challenge because once you oversize the battery to meet those cycle lives or calendar life, you end up with increase in the upfront cost, and that's something that people worry about. This study that we did extensive testing, and this is basically most battery developers have to do that. What we found that the major challenge with those, with calendar aging and even some performance, is due to what's called the SEI layer growth, which is this solid electrolyte interface between the electrode material and the electrolyte. And as that temperature increases, you start growing that layer by depositing more material, and that adds to the impedance growth. In some cases, we also found that upon aging, one of the failure mode is basically the fracture of the particles that leads to the sudden drop or gradual drop of battery performance. There's studies out there that you can probably see that they can actually develop physics-based empirical models or semi-empirical models that can actually help you both predict, but also help with the battery management system adjust over time to optimize the battery life and its performance. And this is something that is essential, and you're going to continue to see more of that as battery chemistry continue to evolve and new materials introduced in the marketplace. When we talk about thermal management of batteries, as you can see here in this graph, this basically, there's two types of active systems that are dominating: the liquid or refrigerant and the air. And then there's pros and cons of each of them, how heavy they are the cost and complexity. But the main thing about both active systems that you see that they have not been able to stop thermal runaway, as I will show in the next few slides. In addition to that, the system, especially liquid, it will consume significant amount of energy from the battery itself to maintain the thermal management within the reasonable operating conditions. We've seen, efficiency drop or drive range drop up to 20%, but if you live in cold areas, and especially those who have electric cars, will notice that the drive range in winter, sub-zero temperature, will drop even by 40, 50%. And that is something that is due to the liquid electrolyte as we described. So what you will see that those are complex systems, which is amazing work that the engineers at the battery technology companies and the automotive have done. I'll just show two examples here. For example, Tesla have those micro channels that actually go around and touch all cells. You're talking about thousands of cells in a Tesla car, and this is, very well designed engineered product to keep the battery within the thermal management condition. Also, for example, in pouch cells, GM to the right here, you see that they have developed those microchannels. These are 2-millimeter cold plates with microchannels that control hundreds of batteries that are connected in series and parallel. As I mentioned before, the challenge here when you have liquid electrolyte, any leak, especially when you have hundreds or tens of sealants in the battery, it's a nightmare for most engineers. It's something that cause for concern, and on top of the energy consumption that is needed to circulate that fluid. I will discuss a little bit to you about the phase change composite solution that we developed at AllCell. It's a combination of graphite and wax. Graphite acts as the matrix that you impregnate or microimpregnate the wax within, and the graphite as a mixer and also as a spreader. Graphite is a conductor, and the wax itself acts as a thermal capacitor, which by absorbing the heat, as you graph to the left, when you heat a battery or any system, that when you have sensible heat only, the temperature continue to increase until you have to stop it. For example, in batteries, when the battery temperature exceeds certain limits, 60 or 70 Celsius, you intend to get into the unsafe zone, and therefore you start throttling down or stop the vehicle from operating. When you have a phase change composite or a phase change material similar to the one we have here, the temperature, once you hit the melting temperature, the materials start transition from solid to liquid and absorb a significant amount of heat in the form of latent heat. That 1-2 punch, which is the graphite moving the heat and the wax absorbing it at the preset temperature, provides you with a passive thermal management that actually elegant, but can be fine-tuned toward diverse chemistries or temperatures that you need. In most cases, you can do it on its own, or very little, let's call it, air system that you can do for extreme conditions, but supplemented the passive thermal management system, but it's going to be much less complex and much less expensive. As you can see, the beauty of this is that by moving the heat around, if you don't have system to do that, like the graph in the middle, the hot cylinders, these are the cells that are without phase change composite. You can see that the temperature exceeds safety limit, and the temperature gradient across the module is actually significant, which in most cases leads to degraded performance and degraded cycle life. However, the one in the bottom middle, you see that with the phase change composite, you spread the heat by the graphite, and then the wax absorb the heat at these preset temperature, and you end up with achieving that thermal management criteria that you're looking for. Here's an example of case study we did. This is a project we worked with a commercial drone company. The company had a battery pack that without thermal management was actually the battery will have to stop because the temperature increased at about with losing about 40% of the capacity that it's in there. Those this is common in those commercial drone application or even electrical vertical takeoff and landing, because you have high demand for power as you take off and land. But we in this application, we added about 8% of phase change composite to the pack, and we're able to extend the runtime by 40%, which is significant for those kind of applications. I'm going to talk about safety lithium-ion batteries, and this is something that is real. That as you look, most time you hear it when you make the cover page or the news, and this is something nobody in the battery business wants to do for this reason. And as we've seen in the past 10, 20 years, that there's significant amount of attention that's paid when those fires take place, whether planes, cars, or even personal electronics. And what's consistent over the last 10, 15 years, studies have shown, and versus investigations shown, that despite the highest quality system, even if you have 6 sigma, what we found, or what the researchers found in most cases, that 1 in a few million cells is going to fail. And this is something that that is proven to be a challenge for the battery industry. Now, what people realize, that while you cannot stop that single cell from going through thermal runaway and cause problems, the focus should be on how can I contain it, that thermal runaway cell, and prevent it from propagating to the rest of the pack and causing fire incidents or thermal runaway incidents that are beyond that single cell. We've done significant studies like others in the past 20, 25 years on how we can actually pinpoint that cell temperature, trigger temperature, which is also in how much heat is generating in that thermal runaway radiation. We've used a device that is very common in the polymer industry, even explosives. It's called the accelerated calorimeter, which is a calorimeter that traces. You can put the cells in there, start heating, and then wait for a period of time looking for any exotherms. If there's no exotherm, you continue to heat and wait and search for those. That's the mode called heat wait search. And then once the exotherm start, as you see in this graph, the calorimeter is designed to follow that and create fully dynamic adiabatic condition that allow you to pinpoint that thermal runaway temperature and also identify the heat rate and thermodynamic information, kinetic information about the reaction itself that allows you to use that in complex models to design solutions around it. We've done extensive tests over the past 10, 15 years on every commercial lithium-ion battery and almost every cylindrical cell in the marketplace. And those are mainly called 18650, which is similar to the one you see in Tesla. And the recent ones are 21700, which is what's Tesla used in the Gigafactory. As you can see here, that most cells have a common thermal runaway temperature, which is above 110, 120. And the maximum temperature that these cells exhibit during that thermal runaway is in most cases over 500 C, and that happened less than a minute of the trigger temperature going haywire. We've developed significant solutions for those, and this is an example of a study that we work with on a workshop at NASA a few years ago on an electric solution or battery solution for electric planes on aerospace application. The study that we did, that what you see here is a battery pack about 40 cells. It's commonly used in electric bike application, scooter application. We have done a study on looking the impact of the material between the cells or their past thermal management. And we tested packs with air, graphite, wax, and even the last one was with our composite, which is a graphite wax solution. The idea here is that we put the cell in thermal runaway by nail penetration of one cell and then look at the impact across the pack and see if the pack can survive those thermal runaway one cell. Here's one test that we've done that you can show that the pack to the left, which has only air between the cells, that once the first cell fills, rapidly goes to thermal runaway and exceeds 600 Celsius in less than a minute. And a few minutes after that, the other cells start popping or start going through thermal runaway, and that's called the domino effect until the whole pack catches fire. The one to the right, as you can see, has a phase change composite, and once that cell goes to thermal runaway, the other cell heat, but we managed to keep them below the threshold, and they go back and cool, and the rest of the pack is safe. Here's a summary of the designs that we've tested. The one to the left is air, graphite only, then wax, and then phase change composite. And as you can see, the effective latent heat and the combination that with high diffusivity is actually what makes the pack safe and what allows us to manage to stop thermal runaway. Here's some autopsy. What you see the pack to the left, which has phase change composite. Once we open it up, you can see that one cell fails, but the rest of the pack is fine, it's still intact. However, the one to the right, you see the domino effect, which once that we actually start pouring water after those cells propagate, so we can stop it from going further. And then you can see here that some of the cells that are really charged after that thermal runaway. Here's pictures of the autopsy of the module. What interesting here, I want to point out a couple of things that we discovered that are critical. One to the left, we found that the nickel cladding or the current collectors on the top actually play a significant factor in providing safety in the pack. The reason is when that one cell is failed, it becomes a short circuit, and the other cells start dumping current in it, which is at significant amount of heating because of ohmic heating of those current that passes, the rush current that passes through those cells. The other thing that we discovered to the right, as you can see, one of the cells are designed to fit from the top. They have a top valve. That's when the electrolyte start going through thermal runaway to avoid explosion, that they vent out of the cells. The mechanism is designed as a fail-safe. However, we found that there's significant issues with the casing, even into metal casing, that there's something that's called side rupture. And the side rupture, basically the electrolyte exit that, and it's like a torch that actually goes directly to the adjacent cells and causes major problems. And those are things that we have to design for. But the one with the current dumping is something that we investigated further. And as you can see here, we found that in those cells that are electrically connected, you see a significant amount of current rush and significant amount of heat of the adjacent cells compared to ones that don't, as shown in this graph, with 2 cells in series and 10 in parallel. And what that tells us that there's something, not just the thermal runaway that happened to the cell, but the current that exactly rushes because of that cell that failed was electroconnected to the rest of the pack, what causes a lot of those heating issues. And that prompted us to do further investigation to understand if the internal cell device, which is called the CID, is capable or not capable of preventing that current dumping. And what we've done, we actually done extensive studies on those CIDs. We took cells and we started short-circuiting them and measuring the current that comes out of them. And what we found continuously, especially at 100% state of charge, that those cells dump significant current. You're talking about a peak of 50 amps or more and a constant current of more than 30 amps for a few minutes, which is enough to drain that cell completely. The reason this is critical because if you don't stop that, you're going to end up with cells temperature exceeding hundreds of degrees and causing major problem across the pack on top of the thermal runaway cell that adds thermal energy. And what we've designed, we have designed what's called fusing. Most companies, battery companies, have a lot of work into that. They have different fusing techniques. And in our case, we designed fusing on both ends of the cells. This is proprietary. This is something that we work on carefully with our suppliers and cell suppliers and our customers. And what you've seen here, when you fuse the cell, that even when a cell failed catastrophically, the other cells, heat up, but they don't go into thermal runaway and they don't exceed because the current dumping has been eliminated, and once the cell is isolated from the rest of the pack. I want to talk to you a little bit about another issue that we've seen, once you stop thermal runaway propagation, which is the flame issue from the electrolyte. And this is something that has been addressed by the industry. Basically, when a cell fails, even if you stop thermal runaway propagation, that flame that comes out of the cell, if it escapes the pack, it could cause fire for the surrounding pack surroundings. And the industry is handling that in the way that we see that's going to be very common is what's the UL recommendation is a new regulation that's called UL 9540A. And what is that said? Basically, for a pack to be safe, you have to do two things. First, you have to prevent the propagation of the cells from one cell to the other in the pack. And the other one, you have to prevent the flame from coming out of the pack itself. We have done testing on this similar packs that we have developed at AllCell, and as you can see, the one to the left, that even if you manage to stop the propagation, you still have that flame coming out of the cell from a single cell, and that is something that is significant. Once you do the PCC or the phase change composite to stop propagation, the other issue, how to handle the flame, and what we developed is a combination of manifolding and also a hydrogel material that can actually help with that flame extinguishing inside the module. Hydrogel are super absorbent polymer. They're very common use in baby diapers. What they do is they can absorb water probably 10 or hundreds of times their weight. And if you put hydrogel with water, sealed in this manifold, basically direct the flame to the hydrogel. So the hydrogel, when actually it's ruptured, it does two things. First, the latent heat evaporation of water in it absorb a lot of energy that allows you to quench that flame. But in addition, the vapor released will dilute the electrolyte that's coming out of the cell. And with the proper venting, you can dilute it and allow it to exit the pack without causing any flames or any problems. And this is work we've been doing for the last couple of years with some of the leading cell manufacturer, and we filed IP on it, and hopefully we're going to get it into commercial products in the next year or two. Finally, I want to just tell you a little bit about a new project we started as part of the Shell Game Changer program. Shell Corporation has funded kind of a competition, nationwide competition that is run by the National Renewable Energy Lab. And this year the challenge was about fast charge. And what we've done, we have developed a new solution, which is called Integrated Battery Thermal Management. And I will explain a little bit that what we're doing with NREL. We started this project early this year to demonstrate the technology. and hopefully build prototypes and have NREL tested and validated at their labs in the next year or so. The technology is a combination of the phase change composite and the thermal management solution we developed in combination with smart electronics and an integrated battery management system that allows us to take advantage of the changed material state of thermal state of charge and be able to dynamically charge or discharge the battery based on those conditions with the use of smart electronics. This is basically dynamic charging. And the reason this is critical because in most applications, smart grid applications, see to the left, if you're able to fast charge the batteries in vehicles using battery buffering, which can is placed strategically between the grid and the EV infrastructure, then you should be able to rapidly charge those applications such as electric plant, material handling, robots, or even electric vehicles without affecting the grid and without affecting the battery cycle life, which is what the technology is about. This is important as we start deploying more electric vehicles, electric powered transportation system, and even stationary. You'll see that that kind of fast charge technology will enable us to be able to meet the requirement of fast charge, but at the same time not adding significant burden in the grid. This is just a summary of some of the work we've done with NREL. As you can see, this is if you have those high energy cells that are used, if you charge those batteries at high C rate, for example, to see the effective temperature is very clear. That if you go just from 35 to 45 C, you should be able to fast charge the battery continuously without degrading life. As you can see, the 135 after 50 cycles fails, but with 2C at higher temperature, you're able to continue to fast charge the battery without any impact. We've done those continuous work collaboration with NREL. We developed those are common RC models, and then we use that to create those model outputs and thermal in combination with characterization to allow us to develop those integrated battery thermal system with BMS and power electronics that allow us to use those batteries and those fast charge application without compromising cycle life and safety. So in conclusion, I would like to emphasize that lithium-ion batteries are leading the way for electric mobility. You're going to continue to see them doing that, especially if the cost continues to reduce or drop in the next few years. Thermal management and safety are still real concerns, and if not addressed properly, they may probably block or hinder for the deployment of lithium-ion batteries. Again, there's new battery technologies that are, we're going to see in the near future, solid state, lithium air, lithium sulfur, but I still believe that they're, while there's continuous interest in development and exciting development, it's going to be at least 5 to 10 years before we see those coming to the mainstream and scaled in high volume. Thank you very much for for listening, and I look forward to the conversation. I'll be happy to take questions as part of this discussion.